个人的时候，在陌生的街头，抬头看着繁星夜垂的天空。I know, I know， 地球另一。
大家好，我是机电105的冯生凯。那今天要跟大家讲的就是这一章节是电池的模型，马克斯韦尔方程式。那首先呢，跟大家复习一些基本的观念。那在这一章呢，首先要跟大家介绍一些就是电磁学的就是一些基本概念，还要复习这样。那就是这个科学呢，用的信念。就是真实复杂的世界要存在优雅、简约的形式来感动人类，啊，就是国威老师的名言。然后接下来呢，就是要讲的呢，就是这个动电会生磁，动磁会生电的概念，就是在一个场域中啊，一个电荷只要运动的话，就会产生磁。那在这个空间中呢，磁的变化也会产生电，对，这是一个相互的作用。简单来说，就是动电生磁，动磁生电，这就是该学科称为电动力学。好，那这个呢，就是我们刚刚讲的动电生磁的概念。这里是一个点电荷，这里一个正的点电荷，然后朝了这边有一个 u 的大小的速度这样子前进的话，然后后面的这个叉叉呢，就是磁场，这样是往里面，叉叉是往里面的一个磁场。那这个点电荷呢往这边运动的话，然后有个磁场向下，那它的受磁力呢就会向上。这是依照一个QV cross B 的一个推导，然后就会产生一个磁力向上。那你的右手做一个旋转的动作，就是先比运动方向，然后再比磁的方向，那就会产生向上的磁力。那再来呢，我们可以间接的讨论到这里这个部分，就是振动呢、非等速啦，然后惯性坐标下物体的变化运动状态。这个呢是老师鼓励我们要念电磁学念20遍，是这样才能进步。然后就是很多大自然中啊，就会很多有偏方反比的定律。这个不管是牛顿力学啊，还是电磁学这边，然后都会产生很多平方反比的定律。那我们等下可以一一做推导。这个呢，就是我们上一个录制的影片中所介绍的。这里是一个空间中的场域，然后这里指的就是通量。这里是通量，就是电场呢跟微小的面积做点击，那这就是通量的概念。再来呢，这里呢就是指的是电力是一个超距力，跟磁力也是一样，就是不需要有介质，然后在空间中就有作用力的一个力，就跟我们那个重力一样。好，这个就是伟大牛顿所发现的重力的定律，这里就是一个平方反比的定律 ，F 等于 R 平方分之 Gms T，这就是一个平方反比的最佳的例证。这个指的就是这个是动力运动学中的牛顿三大运动定律，这个自己去复习，高中都学过了。那再来是高斯定律呢，就是点电荷之间的作用力。OK， 那这里大家可以看一下。再来呢是导体，导体的就是一个物体当中内部具有可动的带电的粒子。就是那这些电子呢就可以随意的运动，然后就可以产生电流，就是一个导体。 那绝缘体的话呢，就是没有具备这个带电的例子，就是有电源，就算有外界电源，也没有办法产生电流。好，那我的复习的部分呢，我就介绍到这边。那接下来是第三章，马克思韦尔方程式，总共有4条，总共是高斯定律、法拉第定律，还有第3条和第4条安培的马克思韦尔定律。那这个部分呢，就是我们下一个同学来做介绍。
Hello everyone, this is Ken from Taiwan Normal University, second grade. Hello, 大家好，我是黄玉凯，来自台湾国立师范大学，基电系2年级。Now, today's topic we're going to talk about the 4 big Maxwell's equations. Now, we first have 2 Gauss's law. One is for the electric, and the second is for magnetism. And then the other is the Faraday's law of electromagnetic induction. And finally, we have the Ampere-Maxwell's law. To modificate the Ampere's law, use of displacement current. First, we're going to head back into history. Let's talk about Maxwell's equations. It is said to be a set of partial differential equations, together with the Lorentz force law, form the foundation of classical electrodynamics, classical optics, and electric circuits. These fields, in turn, underlie modern electrical and communications technologies. Maxwell's equations describe how electric and magnetic fields are generated and altered by each other, and by charges and currents. They are named after the great Scottish physicist and mathematician James Clerk Maxwell, who published an early form of those equations between 1861 and 1862. Now, since the mid-20th century, it has been understood that Maxwell's equations are not exact laws of the universe, but are classical approximation to the more accurate and fundamental theory of quantum electrodynamics. In most cases, though, quantum deviations from Maxwell's equations are immeasurably small. Exceptions occur when the particle nature of light is important or for very long electric fields. Okay, now, we're going to head to our basic topic, the Gauss's law. Now, let's turn our page to 42. No, not 42. Not 43. Okay, now this is the page we're going to talk about. Now, let's look at the left-hand side, Gauss's law for electric field. Now, this describes the relationship between a static electric field and the electric charges that cause it. The static electric field points away from positive charges and toward negative charges. In the field light description, electric field lines begin only at positive electric charges and end only at negative electric charges. Counting the number of field lines, meaning in Chinese 散发力线程度, is therefore yields the total charge, including Bond's charge due to polarization of material enclosed by that surface divided by dielectricity of free space, meaning in Chinese 来源电荷密度, the vacuum permittivity. More technically, it relates the electric flux through any hypothetical closed Gaussian surface to the enclosed electric charge. Sorry for that. And next, we're going to talk about the Gauss's law for magnetism at the right-hand side. Okay, that states that there are no magnetic charges. Okay, we see that equation finally leads us to 0. That is also called magnetic monopoles, analogous to electric charges. Instead, the magnetic field due to materials is generated by a configuration called a dipole. We might learn a lot of it from the circle. Magnetic dipoles are best represented as loops of currents but resemble positive and negative magnetic charges, inseparably bound together. Having no net magnetic charge in terms of field lines, this equation states that magnetic field lines neither begin nor end, but make loops or extend to infinity and back. In other words, any magnetic field line that enters a given volume must somewhere exit that volume. Equivalent technical statements are that the sum total magnetic flux through any Gaussian surface is zero, or that the magnetic field is a solenoidal vector field. That's the end of it. And next we're going to head to Faraday's law. The Maxwell-Faraday's equation version of Faraday's law describes how a time-varying magnetic field creates, or you can say it induces, electric field. This dynamically introduced electric field has closed field lines just as the magnetic field, if not superposed by a static charge-induced electric field. This aspect of electromagnetic induction is the operating principle behind any electric generators. For example, a rotating bar magnet creates a changing magnetic field, which in turn generates an electric field in a nearby wire. That's the meaning in Chinese, that 直生电. Everybody up to me? Well, let's continue to the Ampere's law in Maxwell's addition. Well, it states that magnetic fields can be generated in two ways. One is by electrical current. This was the original Ampere's law. And by changing the electric field. And this was the Maxwell's addition. Maxwell's addition to Ampere's law is particularly important. It shows that not only does a changing magnetic field induce an electric field, but also changing electric field induces a magnetic field. Therefore, these equations allow self-sustaining electromagnetic waves to travel through empty space. Okay, the speed calculated for electromagnetic waves, in Chinese meaning 位移电流, which could be predicted from experiments on charges and currents, exactly matches to the speed of the light, 光速. Indeed, light is one form of electromagnetic radiation, like the X-rays, radio waves. Maxwell understood the connection between electromagnetic waves and light in 1861, thereby unifying the theories of electromagnetism and optics. Okay, that's the end of the introduction of the four big Maxwell's equations. Thank you, everybody.